welcome back to week 7 of the problem solving session for the course Thermodynamics. And in this week, I will discuss one problem regarding the properties of pure substances or or the properties of the liquid vapor mixture inside the vapor dome. So I will discuss about that. Specifically, I will discuss a problem that was discussed by Professor Anand in the lectures where the steam was at a superheated state. So I don't recall me discussing about such kind of problems in the previous session. So I will discuss one problem, briefly go through the solution method, and then we will focus upon the main topic for this week's session, that is the steady flow energy equation. Okay. So I think I can start. Let's see if other students join, else we can just go ahead with it. Okay. Okay, then I guess we can start. So the problem is regarding the problem is given by this given here, a closed rigid vessel. So the keyword is again a closed rigid vessel contains 1 meter cube of steam at 7 bar and 500 degrees Celsius. So the pressure and the temperature of the steam is given. The steam is now cooled to a state where the pressure is 0.5 bar. So we can consider this to be the initial condition, this to be the final condition. Okay, initial state or the final state. Determine the temperature at which the condensation may first occur. Okay, so we need to find the temperature at which the steam will start condense. Okay, or basically the saturation temperature of the particular steam that we have in our particular state of the steam that we have in our hand. Okay, then the fraction or total mass that will condense. So the B would basically, in B we need to basically find the quality of the steam. Okay, and C, the volume occupied by the saturated liquid at the final state. So we will find the volume of the saturated liquid in the final state, that is at 0.5 bar. Okay, so just 1 second. Okay, so we have V1 equal to 1 meter cube, P1 equal to 7 bar or 0.7 megapascal. I'm just converting it so that it is easy to find these values from the steam table, because most of the pressure values are given usually in megapascal, so we need to convert it into it. And T1 equal to 500 degrees Celsius, and P2 is given to be 0.5 bar or 0.05 megapascal. Okay, so if you have steam table, let us directly go to the steam table now. So for that I would like you to find the state of the liquid vapor mixture at P equals 7 bar. So kindly go to the steam table for pressure equals 7 bar and find the corresponding saturation temperature. Okay, don't go don't go through everything that is written on screen. I would like you to do the exercise. So go to the steam table and find the pressure, find the steam at the pressure of 7 bar and find the corresponding saturation temperature. Okay, okay, so if you look into it, you will find that the saturation temperature corresponding to P equals 7 bar is 151.2 degrees Celsius, which is less than the temperature at which our current steam is at, right? It is at 500 degrees Celsius. So by that you can easily imply that since the temperature of the steam is greater than the saturation temperature for the corresponding pressure, so the steam will be at superheated condition. Okay, I hope that is clear. Since the temperature of the steam is greater than the corresponding saturation temperature for that particular pressure, that's why the steam is at superheated condition. Okay, so now we can go to the superheated steam table, and then find the corresponding thermodynamic properties of the steam at P equal to 7 bar and T equal to 500 degrees Celsius. Okay, so kindly go to the superheated steam table and then find the corresponding thermodynamic properties at 500 degrees Celsius for P equal to 0.7 megapascal. Okay. So meanwhile you do that, let me draw the TV diagram so that the analysis becomes more understandable. Okay, so this is the TV diagram and this is the liquid vapor dome. Again, it is slightly skewed towards the left. I have explained it already why it happens, so you can just revisit the lectures or the problem solving session to previous week's problem solving session to find out why this skewness in the curve occurs. Okay, so we know that the critical temperature of the of for water is 374 degrees Celsius. Okay, and the temperature that we have in our hand is 500 degrees Celsius. So it is well beyond the critical temperature. So we can label the 500 degrees Celsius isotherm as this, and the isobar for P equals 0.7 megapascal can be drawn is drawn here. So the intersection between the isobar of 0.7 megapascal and the isotherm of 500 degrees Celsius would denote our initial state, okay, of P equal to 0.7 megapascal and T equal to 500 degrees Celsius. So now it is told that the process is undertaken in a rigid container, so the volume is constant, and that's a very crucial part to solve, crucial knowledge given to us to solve this problem or approach this problem. Okay, so we have that the problem let me go back. The container is closed and rigid, so the pressure the process of process through which the steam has gone from 7 bar to 0.5 bar is isochoric or a constant volume process. Okay, so we can draw a straight line because this is a TV diagram, so we can draw a straight line downwards and reach up to a point up to the saturation vapor line. Okay, because it is the point at which the steam will start to condense. Okay, so once we reach there, we can draw a corresponding iso bar to indicate the point at which the steam will just start to condense. Okay, and remember, this is not the final point. Final point will be somewhere even far below, and we do not know whether this is the final point or this is the final point. So let us consider that the final point and the point at which the steam starts to condense are different. So we will take the final point as somewhat below. Just I'm saying, for instance, we can take it to be somewhere below the state at which the steam will start to condense, and take that corresponding isobar to be 0.05 megapascal, that is already given. Okay, so and we indicate it as the final state. Okay, and in all these steps, the volume or the specific volume as well are constant, right? Because the volume is constant because the process is isochoric, and the mass of the steam is constant because the system is closed. So the volume by mass will also be constant. So the specific volume is also constant, which we found out from the superheated steam table to be 0.51765 meter cube per kg, and the corresponding internal energy is 3127.4 kilojoule per kg, and the corresponding enthalpy is 3482.35 kilojoule per kg. Okay, so from here we can easily find the value of the mass of the steam within the system. So the volume of the container is 1 meter cube as it was already given, and the corresponding specific volume of the steam at the initial state of 0.7 megapascal and 500 degrees Celsius is 0.51765. Then the mass of the steam is 1.93 kg. Okay, and this will remain constant throughout the process. Okay, so first, so we need to find the state at which the steam will just start to condense. Okay, so we need to find the saturation. We need to find the temperature at this point, or the saturation temperature at this point. So basically we need to find the saturation temperature for steam which has a specific volume of 0.51765. Okay, so if you go to the steam table, what you need to do right now is go to the steam table, find the now go to the steam table, not the superheated region but the saturation state. Okay, go to the steam table of the saturation state, find the specific volume of 0.51765 or some volume close to it, and then see whether you get it or not. So if you directly get 0.517, in fact that is fine, but if you do not get, then you need to interpolate. Okay, so in my case, I didn't get the volume of the steam to be exactly as 0.51765 in the steam table, so I needed to interpolate the values. Okay, so the value of the corresponding saturation temperature for the given specific volume lie between these two specific volumes of 0.5085 and 0.6680. Okay, so understandably I need to do the interpolation, linear interpolation in this case. So I find that for T equal to 130 degrees Celsius, the corresponding specific volume is 0.6680 meter cube per kg. Okay, then for saturation temperature 140 degrees Celsius, the corresponding specific volume is 0.5085. Okay, and so our specific volume lies within these two values. So our saturation temperature can also be found out, which will ideally lie between these two temperature ranges, and we can find it using the linear interpolation. Okay, so let's just do it. I will not go through the steps of linear interpolation once again because I have explained it very nicely in the previous problem solving session, and Professor Anand has also done it again in the lectures. So I would rather recommend that you go through the lectures again to clarify your doubts regarding the interpolation, if at all there is anything. Okay, so from linear interpolation we find that the corresponding saturation temperature for a specific volume of 0.51765 is 139.42 degrees Celsius. Okay, and this is the temperature at which the condensation may first occur. And from this saturation temperature value, you can find a corresponding saturation pressure as well, and it is found to be equivalent to 0.36 megapascal. Okay, and that's why I labeled it here. I'm not saying equal, I'm just saying equivalent. I'm not done interpolation. I've just taken the value of the saturation pressure for T equal to 140 degrees Celsius because it's close to the saturation temperature for our corresponding specific volume. So I've just taken P to be 0.36 megapascal, and that's why I've just written it equivalent. Okay, not exactly equal. Now let's see. So the second part of the question is, the first part is done. This 139 point, let me just go back to it, 139.42 degrees Celsius. So the answer to the first question is 139.42 degrees Celsius. Okay, so the second part of the question is the fraction of total mass that will condense. So we need to find the quality of the steam. So quality of the steam basically gives us the mass of the gas, mass of the fraction of the gas in the mixture. So what we need to find is the mass of the liquid in the fraction of the mixture. Okay, so once you find the quality, just do 1 minus the given quality and you will find the quantity of the liquid in the mixture. Okay, that is what we need to find. So so again we need to go to the steam table and find the corresponding values of the corresponding thermodynamic properties at P equal to 0.05 megapascal, and we need to check whether our given specific volume lies within the range of Vg and Vf for this given pressure. Okay, so let's go to the steam table for 0.05 megapascal. So I'll give you some time to look into it and find the values of the specific volume of fluid Vf and the specific volume of the gas Vg at pressure P equal to 0.05 megapascal. Okay, so please kindly do the exercise. I'll wait for some time and then we can cross check our results. Okay, so better I would just hide it here. So go to the steam table for P equal to 0.05 megapascal and find the corresponding values of Vf and Vg and check whether this V that we have in our hand lies within Vf or Vg. Okay, it's very crucial. And logically speaking, it will, because we found that for 0.3 megapascal it is at the saturation vapor line. Okay, so this is basically where the steam will start to condense, or steam will tend to have some moisture, tend to accumulate some moisture, right? So if we go below 0.3 pascal, just the 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 steam is bound to have higher level of moistures. Okay, so it will obviously lie within VF and VG, but still it's a good exercise to do. So once you do it, you will find that VF is 0.00010 meter cube per kg, and VG is 3.3625 meter cube per kg, and our given specific volume of 0.51765 lies well within this range. Okay, so we will have V1, right? We will have V1 as 0.51765 meter cube per kg. So from this equation, you can easily find the value of X, that is the quality of the steam. So once you substitute the value of Vg and Vf and V1 in this equation, you will get that X is equal to 0.1536 or 15.36%. It is a, what's this? It is the mass of the gas in the liquid vapor mixture, okay, or mass of the vapor in the liquid vapor mixture. So once you know this, you can easily find the total mass that is mass of the mixture that is condensed. So we need to find the value of the fluid, mass of the fluid in the liquid vapor mixture. Okay, so once you do it, you will find that it is equal to 0.8464 or 84.64%. Okay, so the final question is, final part is, the question is volume occupied by the saturated liquid at the final state. So we need to find the volume of this particular condensed liquid in the final state. So it's quite easy now, because since you know the mass of the fluid that has condensed, you can easily find the volume of the total volume of the fluid that has been condensed. So it can be found out by this equation, mf into vf, that is specific volume of fluid. So that is also known, and this also known, so you can easily now find out. So you can find out this by just multiplying the fraction of the fluid in the mixture into the total mass, that is 1.93. So we will get this, and it is already known once you found out this for P equals 0.05 megapascal, and once you do the calculations, you will find that the total volume of the fluid in the mixture, not the specific volume, okay, the total volume of the fluid in the liquid vapor mixture is 0.00168 meter cube. Okay, so I'll wait for a few 1 minute just for you to verify your answers. So I'll keep it in such so that most of the solutions are visible, so you can cross verify your answers and go back to the steam tables as well to verify the values and just see whether you understand it or not. Okay, okay, so now I guess we can proceed. So let us, so I will again leave this question. It's a very good example actually. The question is regarding determining the value of the specific volume of water at 20 megapascal and 400 degrees Celsius in meter cube. So this is an interesting question. It is to determine the specific volume of water at 20 megapascal and 400 degrees Celsius in meter cube per kg using the steam tables, then the ideal gas equation, and the generalized compressibility charts. Okay, so this is a very interesting exercise. So it was done by Professor Anand in the lectures. So I would suggest you to go through the example once again. For the sake of saving time, I'm not going through the example again here, but it's a very interesting example. Okay, to understand the variation in the accuracy of the results, specifically between why we use steam tables to determine the properties of steam rather than using the ideal gas equation. Okay, so okay, let us just go through it once. I will quickly go through it. I will go through the first two parts and I will leave you leave the part C as an exercise. So at P equal to 20 megapascal and 400 degrees, at P equal to 20 megapascal, you can go to the steam tables and find out the corresponding saturation temperature. So once you do that, you will find that the corresponding saturation temperature for P equal to 20 megapascal is 365.8 degrees Celsius. And since 400 degrees Celsius is greater than the saturation temperature for the corresponding saturation pressure, it means that the steam is at the superheated region. Okay, so thus we need to go to the superheated steam table to find out the properties of the steam, corresponding thermodynamic properties of the steam, and we can find it using the superheated steam table. Okay, and once you do that, you'll find that for P equal to 20 megapascal and T equal to 400 degrees Celsius, the corresponding value of the Vf, small vf, that is the specific volume of fluid, is 0.00995 meter cube per kg. Okay, so it was quite simple. It's just looking through the steam tables and the superheated tables to find out the values of Vf. Now we find out the same value using the ideal gas equation. Okay, assuming that we can treat the steam at the superheated region as an ideal gas, because we also read that far away from the saturation vapor line, we can treat the water vapor as ideal gases. Okay, it was one of the conclusions in our previous session. So keeping that idea in mind, so let us assume that the given state, superheated state of the steam, can be treated as an ideal gas. So let us use the ideal gas to find the value of the specific volume of the fluid. Okay, so to do that, we use the ideal gas equation, or we can just simplify it to P into small v equal to RT, where R is the universal gas constant by the molar mass of water. So after doing that, we find that the value of R for or specific gas constant for the steam is, for water, is 0.4619 kilojoule per kg Kelvin. Okay, so the specific volume V can be found out by RT by P. So once you substitute the value of the specific gas constant, the temperature at the absolute scale, and the pressure, you find that V is equal to 0.015543 meter cube per kg, which has a lot of errors compared to the given value of Vf, which you found out from the steam table. Okay, so that's why we usually don't use the ideal gas law to find out the corresponding thermodynamic properties for the steam. Okay, but if it was, say, for example, 4000 degrees Celsius, or say 1000 degrees Celsius, in that case you might be able to use the ideal gas equation or approximate to find approximate values of the thermodynamic properties of the steam at that very high temperature. But at temperatures close to the corresponding saturation temperature, you can clearly see that 400 degrees Celsius is quite close to the saturation temperature at P equal to 20 megapascal. So at this range, it is advisable not to use the ideal gas equation to find the properties of steam using the it is not advisable to use the ideal gas equation to find the properties of the steam at this range. Okay then, so now I guess we can start the main topic of interest for this week's session, that is the steady flow energy equation. So again, as per our usual agenda, I will not go through the entire derivations. I'll just briefly go through the steps and mainly focus on the application of our final result, that is the steady flow energy equation. Okay, so let us go through it once. I'll quickly go through the derivation, and then we can start solving the problems for this week. Okay, so from the first law of thermodynamics, we have dE is equal to delta Q minus delta W. Okay, this is the first law of thermodynamics for any thermodynamic process. Okay, or delta E is equal to Q minus W. Or we can now dissociate the energy into the internal energy, the kinetic energy, and the potential energy. Okay, so if we divide this equation by delta t and take the limit of delta t tending to 0, we will find the rate equation for the first law, that is q dot equal to q dot equal to dE by dt for the control mass plus the rate of work done. Okay, so this is in the form of rate equation. Basically the units are now in watt or joule per second. Okay, so the units in this equation is in joules, but in this joules or kilojoules, but in this equation the units are in the form of watt or uh, kilojoule per second or joule per second. Okay, so this was one of the example discussed by Professor Anand regarding the application of the rate equation for the first law, uh, which is for analyzing the net work done by a light bulb that has been operated for a long time. Okay, it's very important. The long time, the term is very important because it implies that the bulb has reached a steady state, because when initially you switch on the bulb, there will be a change in the temperature of the bulb, right? Because the filament that yeah, that gets that produces the light has to heat up for certain amount of time, and then only it achieves a steady state and then produces the light. Okay, so given that the bulb has stayed on for a long time, we can assume that the net rate of energy transfer in the bulb achieves a steady state. Okay, so the net rate of change of energy in the bulb is equal to 0 because it has achieved a steady state. So the net heat emitted by the bulb would be equal to the net electrical work that is being done on the bulb. Okay, so in the case of to find the net electrical work done on the bulb, we can use this equation. So net work done, we know the equation for net work done, that is V into I into T, or I square RT using the Ohm's law. Anything we can use. So right now we just use that is given in the lecture. The W is equal to V into I into T, and to find the net rate of work done, we just divide it by T to find that W dot is equal to V into I. It is the net rate of work done in the bulb, and this would be equal to Q dot. It is the net rate of heat dissipation from the bulb because of the electrical work input. Okay, and then there is the principle of mass conservation, and like if any one of you have taken the fluid mechanics course, so you will see that this is one of the fundamental laws that is being taken into consideration for analyzing fluid mechanics problems. And from that we can basically say that mass is neither created or nor destroyed. So if we achieve a steady state, that is the rate of if there is no mass accumulation in the system, that is basically if there is no way in which mass is being accumulated in the system, then this term will go to 0. Okay, Professor Anand has taken a very good example that if we take a bucket in hand, let me just draw the example. If we have a bucket in our hand and we turn on the tape, okay, and water will flow down, right? And assume that there is a small hole in the bucket from where the liquid tries to sip out in the form of small droplets. Okay, and so what do you think would happen to the level of water in the bucket? Can you please tell? Like, will it go up, will it go down, or remain constant, or remain constant, given that the flow rate from the tape is much more higher than the flow rate that is oozing out from the hole below the bucket? You can write in the chat box. This was discussed by Professor Anand in the lectures. Okay, so down, water level would go down. Okay, oh, see, the thing is, take into the this fact into consideration that the flow rate from the tape is, say, just give an example, 0.5 meter cube per second. It's a very random value, okay? Just don't take it to be very serious. Don't take it to be the actual value of the mass flow rate from a tape in any bathroom or anywhere. Don't take it as a real value, okay? I'm just giving a generic, a very random value to the flow rate, and take that the flow rate from the exit is 0.005 meter cube per second. Okay, so now what do you think would happen to the level of water? I already told that the level, the volume flow rate of the water from the hole below is much more lesser than the volume flow rate of the water from the tape which is filling up the bucket. So what will happen to the level of water in the bucket now? Like, this is continuously flowing in and this is continuously flowing out, but this volume flow rate is much more lesser than the volume flow rate from the tape. Uh, so if you think that, what would actually happen is that the water level would go up. Okay, you can even try out this experiment. No need to do it with a bucket, but just take a small glass of water, plastic glass, disposable glass, poke a small hole in the bottom of the glass and take it to a tape and turn on the tape. So you will see that of course there will be some water droplets coming out of the bottom of the glass, but you will see that eventually the glass will fill up and overflow, even if there is a water flowing out from the bottom of the glass. Okay, primarily because of the fact that the input rate of water is much more higher than the output of water from the whole of the glass, and thus the water will get accumulated in the glass, right? So similar concept we can apply in the mass conservation as well. So this dm by dt cv would implies that the rate of accumulation of mass in the control volume, right? And that would be equal to the summation of all the mass flow rate coming into the control volume minus the summation of all the mass flow rate going out of the control volume. Okay, because why this is positive? Because this will contribute to the increase in the mass within the control volume, and this will contribute to the decrease in the mass of the control volume, right? So if these two are not equal, then there would be a mass accumulation or mass reduction in the control volume. Similarly, if there's only one inlet or one outlet, we can disregard this summation sign and take it to be dm by dt cv equal to m dot I minus m dot e. So if m dot I is much higher than m dot e, then this term will go up. If m dot e is much higher than m dot I, then this term will go down. And if both of them are equal, then this will be equal to 0, right? That is what basically happens in the case of pipes, right? If we take a pipe into consideration and take a particular cross section for our analysis, so let me just draw it. Let me take a particular region of the pipe for our consideration. So you will find that if this is m dot I and this is m dot e, you will find that m dot I is always equal to m dot e. Okay, and that's why there is no mass accumulation within the pipe, and the flow continuously occurs without any stoppage. Even if there is some destruction to the pipe, or there are some disturbances or blockage in the pipe, then the flow will stop. But ideally there is no blockage in the pipe because of this fact that the net mass input to the pipe is equal to the net mass output through the pipe for a particular given cross section. Okay, I hope this was clear. Okay, so again, this is the formula for finding the mass flow rate. It is given by rho a into v, where v is the volume of, where v is the velocity of the flow, a is the area of cross section through which the flow is occurring, and rho is the density of the fluid. Okay, this is quite simple, and I'm just reading it out so that you're not confused with the terminology. So don't get confused with v for volume. So here it is specifically given as a vector that will imply that this is the velocity. Okay, so capital V without any vector sign is volume, small v is specific volume, and bold V or with vectors or with vector sign is velocity. Okay, so there are lots of V in this analysis, so students might get confused sometimes. So I'm just pointing it out beforehand, and if there's any confusion in the derivations, just let me know. Okay, of course I will not go to derivation, but say when we are solving problems and you are confused with any terms in the question, you can just stop me and ask. Okay, so again, now uh, we discussed about the first law of thermodynamics for a control volume, or in this case it is basically where there is a continuous inflow and outflow of mass through the given control volume. Okay, so the major difference that comes into picture while determining or understanding these kinds of systems is that in the first law now we need to take into consideration of the mass flux and the flux energy flux that comes in and goes out of the control volume. Okay, and one more terminology that is very important, it is the flow work. Okay, that is given by this equation. Okay, so how it is derived, I won't go through it, but it is advisable that if you have any doubt, just go to the lectures by Professor Anand to know how this happens. It's very simple actually. The net work done is given by net rate of work done is given by force into velocity. So we can dissociate force into P into A, that is pressure into the area. So we dissociate into PV into dA, right? We dissociate into PdA and we keep it as V, or we can take the magnitude into consideration. So we keep it as V. Okay. So once you do that, you'll find that V dot dA now can be taken as V dot. Okay, it's just a manipulation by using the principle of dimension analysis. So let me just try to do it for you here. So if we take V into dA, so the units of V would be meter per second, and units of area is meter square, right? So if we take this into consideration, this multiply this and write it in this manner, so it becomes meter cube per second, or rate of change of volume per second, right? So we can write it as capital V dot. So from there only this comes into picture. Okay, and how now capital V can again be written in the form of specific volume, so it becomes P into small volume into the net uh, mass flow rate. Okay, again there are very intricacies while deriving these equations, but just for the sake of that this is an introductory course, I am just simplifying the derivation method in this manner. Okay, so the flow work per unit mass can be given as E plus PV, because now the flow work will come into picture, and E is already the net energy transfer that occurs in the fluid, right? So we just need to add the flow work in the terminologies to have that the net flow work per unit mass would be E plus PV, where P is the pressure and V is the specific volume. So it can be written as U plus PV plus half V square, where V is the velocity now, and plus dz, which is the potential energy. So we can again write U plus PV is equal to H as the enthalpy. It we already defined while discussing the first law. So we get that the net flow work is equal to H plus half V square plus dz. Okay. So the net rate of change of energy in the control volume can be given by Q dot CV minus W dot CV plus the net influx of energy. Okay, this is the net influx of energy, that is M dot I plus HI plus VI square by 2 plus DZI plus the net, sorry, this should be minus sign, I'm sorry for the confusion, minus the net outflow of energy, that is M dot E plus multiplied by HE plus VE square by 2 plus DZE. Okay, and this net work flow work is taken into consideration by incorporating the net enthalpy rather than the internal energy. Okay, so for a control volume having multiple inlets and outlets, we can write the Serif energy equation as dE dt for a control volume as q dot cv minus w dot cv plus summation of the net energy influx m dot I into hi plus vi square by 2 plus dzi. Again, I'm sorry for the confusion, this will be a minus sign, minus the summation of the net energy outflux or efflux, that is m dot E into he plus ve square by 2 plus gze. Okay, so I hope the basic form of the steady flow energy equation is quite clear. So of course right now you don't need to know the entire derivation, but if you want you can know, and Professor Anand has very nicely done it in the lectures. But the very form itself, I hope it is clear, the terminologies involved in the equation is clear. You can just say yes or no, then we can go ahead and solve some problems regarding it. Otherwise, if you have confusion in the terminology, then it will be difficult to move ahead. Are all the terms in the steady flow energy equation clear? Enthalpy, velocity, kinetic energy, potential energy, mass flow rate. Yes, thank you so much. Okay, so this is okay. So we have some certain simplification that can be done to the steady flow energy equation. So given that the, the system achieves a steady state, oh I'm sorry, this is ideally known as the first law of thermodynamics for a control volume. Okay, first law of thermodynamics for a control volume. This becomes the steady flow energy equation once we assume that the net rate of change of energy in the control volume is equal to 0, right? So once this is equal to 0, we can simplify the equation further as q dot minus w dot plus the summation of m dot I hi plus vi square by 2 plus dzi minus summation of m dot t into he plus v square by 2 plus dzi, and that will be equal to 0. So this is simplified further, and this form of equation for this being equal to 0 is known as the steady flow energy equation. Okay, or steady flow energy equation, whatever it may be. So I like to give an acronym of SFEE. In the lectures it is maybe written as SSSF energy equation, but for me I like the acronym of SFE, so I will more or less try to mention it as SFE all the time. Okay, similarly the mass conservation, as I mentioned, if there is no accumulation of mass in the control system, we can take dm by dt for the control volume be equal to 0. So we will have summation of m dot I minus m dot t equal to 0, or summation of m dot I is equal to m dot e. For single inlet and outlet, we will have mi is equal to me. The net input of mass is equal to net output or outflow of mass, that will be equal to m dot, right? We equate m dot I and m dot e to a particular m dot, so we can use that. And once you divide, now if we have this equation in our hand, and once you divide m dot with all the terms here, you will get q minus w, where small q denotes the net heat generated by the net heat input to the system per unit mass. Small w is the net work output from the system per unit mass, and all these terms now would be in the form of per unit mass. Okay, so hi would be kilojoule in the units of energy per unit mass, vi square by 2, it is kinetic energy per unit mass, gz is the potential energy per unit mass. Okay, so now we look into some further simplification to the steady flow energy equation. So first example was the example of adiabatic throttling process. Okay, so in the case of a throttling process, where the flow is abruptly put into rest by using a throttling device, in that case there is, since the process is adiabatic, there is no heat interaction. Okay, and since the process is steady, so this term will already go to 0, and in throttling process ideally there is no additional work done. Okay, so the work done term is also equal to 0. So we have these terms in our hand. Okay, so for steady state, again m dot I or equal to m dot e is equal to m dot. Okay, so we can divide all the terms by m dot to have hi is equal to he plus ve square minus vi square plus gze minus zi. Okay, just keep HI here and take all the terms in the left hand side, so we will get this from the equation. Okay, so usually in most of the cases where we use the apply the, or use the throttling devices, the net change in the potential energy is almost equal to zero. Okay, or if we say assume that the throttling device is placed such that the inlet and outlet are at the same determined height level, then this change in potential energy is zero. Or even if we consider the fact that there is a certain change in the height of the inlet and outlet, this change in the potential energy due to the change in the height of the inlet and outlet is usually much more lesser than the net enthalpy or net magnitude of the net enthalpy of the process. Okay, that's why this is equal to 0. We can take this to be equal to 0 for most of the cases. Moreover, for further simplification, if not specifically mentioned in the process, we can take the net change in the kinetic energy of the process, kinetic energy of the flow, to be also equal to almost equal to 0. I am not saying that this is equal to 0, but the very fact that the magnitude of the enthalpies of these processes HI and HE are much more greater than the net change in the kinetic energy. Okay, similarly, they are also much more greater than the net change in the potential energy. So that's why we can take the net change in the velocity as also equal to 0 compared to the magnitude of the enthalpy in the process. So for an adiabatic throttling process, the steady flow energy equation takes the form of HI equal to HE. Okay, or the net change in the enthalpy of the process as equal to 0. Okay, or basically H equal to constant for an adiabatic throttling process. Okay, this is for an ideal throttling process, the enthalpy remains constant. This is one of the important forms of the SFE or the steady flow energy equation that we need to take into consideration. Okay, next is turbines and rotary compressors. Okay, so we know that the net application of a turbine or a compressor is as a work producing or a work generating device, right? A turbine would produce work and a compressor would consume work to achieve the required process. Then we need to basically, if we use compressor to fill up air in a football or a cycle, or we need to run a device using highly pressurized air, then we need to give a work input to the compressor to generate that additional to achieve that particular process, right? So as I mentioned, then compressor is a work consuming device and turbine is a work producing device. So the key thing to note here is that the work done term will not be equal to 0, because this is the term that is of huge interest in the case of turbines and compressors, right? So considering again that these systems, that is turbines and compressors, achieve a steady state, then the net change in the energy of the control volume is equal to 0. So we take it to be 0. Then considering that these are insulated, or net heat interaction is almost equal to 0, the Q dot term can also be taken as 0. Okay, so term that we have in our hand is now W and net energy influx and outflux. Okay, again sorry, this is minus, not plus. Okay, so for mass conservation, for steady state, summation of m dot I minus summation of m dot E would be equal to 0, or mi would be equal to me. So if we now substitute this in this equation, or take it as equal to m dot, some m dot, then we will have minus w dot plus m dot hi plus vi square by 2 plus gzi minus m dot he plus v square by 2 plus gze. Then we will have w dot, we take the net work done term, in the left hand side, this will become positive. So we have w dot is equal to m dot hi minus he plus m dot vi square minus v square by 2 minus mg zi minus zi. So again, in this case, you will see that the terms of interest are the enthalpy and the net work output. So this is the most crucial part, but you will see that again that the magnitude of the net change in the enthalpy is much more greater than the net change in the kinetic energy and the potential energies. I am not saying that these are equal to 0, but compared to the net change in enthalpy, these are almost equal to, or very very small. That's why, as an approximation, we can cancel out these terms, or disregard these terms. So we will have that the net work done by a turbine, or work done by a turbine, would be equal to m dot hi minus he, and in the case of compressor, this sign will just be interchanged. It will become he minus hi. Okay, because we are in giving a work input to the system, so the net enthalpy at the exit will be higher than the enthalpy at the inlet. So this will become work done. Sorry, work done would become he minus hi into the mass for a compressor. Okay, I hope this was clear. The throttling process and the turbines and compressors, the steady flow energy equation simplification for the throttling process and the, yes, thank you so much. Now, in the case of nozzles and diffusers, again, uh, the main function of nozzles and diffusers are to say achieve a higher velocity or lower pressure. Okay, so there is an interplay between the velocity and pressure in the case of nozzles and diffusers. So we cannot now disregard the change in the velocity as we have done in the previous two cases. Okay, so the main thing is we need to know that what's the main purpose of the device that we are using and where we are applying the steady flow energy equation. Okay, so the good practice is to write the entire equation first and then disregard the terms that can be neglected, and then play with the remaining terms that we have in our hand, and then again see how much further we can simplify it, and then finally obtain the governing equation for this particular system, rather than directly assuming the form, or if you are not able to recollect, it's a good practice that you remember the entire form of the steady flow energy equation, and then cancel out the terms that you will eventually realize that are not important. Okay, so in the case of a nozzle and diffuser, as I mentioned, the velocity terms are crucial because the very purpose of using nozzle and diffusers are to increase the velocity or decrease the velocity, or decrease the pressure or increase the pressure. Okay, so we'll have that if we consider the net heat interaction as 0, then q dot would be equal to 0, because we can consider it to be an adiabatic system, so, or insulated system, then the net heat interaction would be equal to 0. Similarly, there is no work done on the nozzles and diffusers, so w dot term can also be taken as 0. If you are considering a steady state process, then the net change in the energy would again be 0, so dE by dt for the control volume is 0. So these three terms can be easily cancelled out. Okay, so terms that we have in our hand are the energy influx and outflux terms. Okay, so since these are 0, we can easily equate them. From that we'll have that hi plus vi square by 2 is equal to he plus ve square by 2 plus gze minus gzi. We just take these two terms to the right hand side. Okay, sorry, we take this to the left hand side, then take this to the again right hand side, so that there is a negative sign here. Okay, so now again you will see that if we consider that the inlet and the outlet are placed in the same height, then the net change in the potential energy will be equal to 0, exactly equal to 0 if they are kept like this, because the net change in the height at the inlet and outlet is 0, right? Moreover, again you will see that even if it is the nozzle and diffuser are tilted, the net change in the potential energy is most of the times much more lesser than the net change in the velocities of the or the enthalpies of the flow. Okay, so this term can be ideally taken to be 0 in the case of nozzles and diffusers. Okay, so we will have that hi plus vi square by 2 is equal to he plus ve square by 2, or hi plus the net inlet enthalpy plus the net kinetic energy at the inlet would be equal to the net outlet enthalpy, or the net plus the net kinetic energy at the outlet or the exit. Okay, so this is the governing equation in the case of, this is the form of the steady flow energy equation in the case of nozzles and diffusers. Okay, and finally we have heat exchangers. Again, this is a very simplified version of the energy equation in the case of heat exchangers. So because heat exchangers themselves are a separate subject of study in mechanical engineering, or a sub subject, or a part of the subject of called heat transfer. So they are very extensive topic of discussion. So we cannot limit the entire analysis of heat exchangers in this form equation. So this is a very simplified version of the actual energy equation that we use to analyze heat exchangers. Okay, but for the sake of an introductory course of thermodynamics, we can analyze heat exchangers using this form of the equation. Okay, so in the case of heat exchangers, again the net uh, heat and work interactions are zero. This which is very interesting, that there is a heat exchanger in the name, and you are saying that there is no heat interaction. So by that I mean that the heat exchange is between the streams of the energy, that is streams of the fluid flow that is being injected in the heat exchanger or taken out of the heat exchanger, rather than the exchange of heat between the uh, setup or the system through which the heat exchange is being obtained. Okay, so what would basically what happens in the case of heat exchangers is that we input a certain stream of fluid that has certain temperature, say hot or cold. Then we input another stream of fluid that is has an opposite uh, range of temperatures of the inlet. So if we are injecting a hot fluid, we will, if we want to exchange the heat, we will expect that we will input another stream of fluid that is colder than the inlet fluid, so that when they interact with each other, there is an exchange of heat between these two streams of fluids that will result in the outcoming fluid to be much more colder than the incoming fluid, because of the exchange of heat between this inlet fluid and another fluid that is being injected to exchange the heat from the stream of the fluid of consideration. Okay, or internally you can assume it such that there is a pipe here that is of our interest. Okay, that contains the fluid of our interest. There is another pipe within the heat exchanger that is in contact with this pipe. Okay, so what will happen is that the fluid of our interest, say a hot water that is being used that is being used by a apparatus, and now we want that hot fluid to be cooled down. So what we'll do is that we'll inject this hot fluid from this green pipe, right? It will pass through this green pipe, and now since we need to cool this fluid down, we'll inject another fluid from another source that is much more colder than this fluid. So this will go inside this pipe, and during this flow they will interact because they are connected. The surfaces of the pipe are connected, so the heat transfer would occur across this pipe. Okay, so let me use different colors. So heat transfer would occur across these pipes, and this fluid, say I will label it, it was hot and it is cold. So this fluid that was initially hot will become colder, so this becomes cold, and this fluid that was initially cold will become hot. Okay, so you can easily see that they have exchanged heat among themselves within the apparatus, right? But what I am saying, that if we are considering this entire apparatus as a system, there is no heat interaction between the surrounding and the system, and that's why Q dot Cv is equal to 0. Okay, then this will be 0, and since there is no additional work input done to the heat exchanger, so this W dot term will also be equal to 0. So again we are left with this energy input and output terms. So you will again find that the net changes in the potential energy and the kinetic energy are usually negligible compared to the net change in enthalpy, because you can clearly now observe these differences, because based on the application itself you will understand what are the terms that are important and what are not. So in the case of heat exchangers, since they are exchanging heat, you will understand that the enthalpy terms will be more important than the potential and the kinetic energy terms, right? So disregarding those terms in hand, so the final form of the energy equation, or the steady flow energy equation for heat exchangers, turns out to be the summation of mi dot hi would be equal to summation of m dot e into he. Right? And in this case now you cannot disregard the summation sign. Why? Because you can clearly see there are multiple inlets and outlets, because there is no point of having a heat exchanger with having only one inlet and one outlet, right? Then through through which how would the fluid exchange heat, right? So there needs to be at least two inlets and two outlets for the heat exchange to occur, right? So we need to take that into consideration, and that's why the summation sign would remain in the case of heat exchangers, right? And this sign was removed in the case of throttling process, so not to get confused with it. So in the case of heat exchangers, the summation sign will remain, and that's why we will have this form of the steady flow energy equation in the case of heat exchangers. In the case of throttling device, we disregard the summation, so we have HI equal to HE, okay, for throttling process. So I hope this was clear. Any doubt up till now? Clear. Okay then. Thank you so much. Then now I guess we can directly go to the questions. Yep. So let us go to the first question. Okay. I hope the question is visible. Since there's only one student today, so I guess we can speed up the problem solving session part, right? It won't be that difficult. Okay. Which of the following statement or statements is true? In an unsteady flow process, the fluid characteristics like velocity, pressure, or density at a special location changes with time. In an unsteady flow process, the fluid characteristics like velocity, pressure, or density changes from one special location to another, but do not change with the passage of time. So which of the statements is or are correct? A, right? So it is correct. So for the case of unsteady process, the fluid characteristic like velocity, pressure, or density will change from different spatial locations. Okay, change at different spatial locations. Second question is, the first law of thermodynamics for a flow process, also known as steady flow energy equation, is valid for which of the following types of fluids? It's an interesting MCQ, so we'll tell the answer. A and B. Okay, so yes, at first I also thought in a similar way, because while we are studying fluid mechanics, say when we are considering the Bernoulli's equation, the incompressible and the inviscid assumptions like come into picture, and that's why I initially also thought that myself thought that this would be the correct answer. But according, if we think deeply, you'll realize that there hasn't been any stage that we have reached yet while deriving the steady flow energy equation where we had to impose that condition that the fluid has to be incompressible or fluid has to be inviscid, right? Because if we go back to the equations, yeah, so if we go, say we have the equation here, sorry, if we look into this equation, while deriving this equation, there is nowhere we have assumed or taken into consideration that the fluid has to be inviscid or incompressible, right? So the assumption has not been imposed yet. I also thought that if we consider the fluid to be inviscid, then we can disregard the viscous dissipation term. But here the viscous dissipation term, or the term that is associated with the heat generation in the case of viscous fluids, is also taken into consideration within this framework. Okay. And moreover, the change in density of the fluid is also not imposed, because we have not told that the density of the fluid has to remain constant. We have not discussed it while deriving the equation. So it is actually the intricacies that we have applied while deriving this equation that allows us to write that all these terminologies would be correct, because till now we have not taken any such assumptions in hand that imposes that the flow has to be incompressible or inviscid while deriving this equation. Okay, so that's why all options are correct. This was a tricky question, that's why I mentioned it. Okay, is it clear? Yes, thank you. Okay, then let us go to the next question. Air flows steadily at the rate of 0.5 kg per second. Okay, so we have m dot in our hand. This is m dot, through an air compressor entering at 7 meter per second velocity V1, 100 kilopascal pressure P1, and 0.95 meter cube per kg volume small v1, leaving at 5 meter per second v2, 700 kilopascal p2, 0.9 meter cube per kg v2. The internal energy of the air leaving is 90 kilojoule per kg, greater than that of air entering. So u2 minus u1 is equal to 90, right? Cooling water in the compressor jackets absorb heat from the air at the rate of 58 kilowatt. Okay, so Q is minus 58 kilowatt. Compute the rate of shaft work input in the air in kilowatt. Okay, so need to find W dot. Okay, so my suggestion would be write the entire steady flow energy equation first. All the values of all the thermodynamic properties are already given both at the inlet and outlet. Just substitute it in the equation and find the value of the net work done. It's very simple actually. All the values are already given. Just need to find W dot. Let me write the equation again. So since it is steady flow energy equation, so it will be 0 equal to, or disregard 0, you can write it as Q dot plus M dot Hi plus Vi is velocity, okay, plus Gzi equal to W dot plus M dot He plus Ve square by 2 plus Gz. All terms are given. Since pressure is given, volume is given, internal energy change is also given, so you can easily find the net change in the enthalpies as well, right? So everything is given, you just need to find W dot. Okay, just substitute the value of everything here and find W dot. Quite simple. I'll give you say 5 minutes. Try it out, tell me the answer. It's not necessary, there might be some mistakes while calculation, but the important thing is to know the how to apply the steady flow energy equation in this kind of problems. Okay, so you can try it out, tell me the answer, let us see whether it matches with the solution that I have in my hand, and that's fine, it's completely fine. I hope the question is clear, right? Just do part A, part B we can do together. Just do part A, it's quite simple. So this would be the form of the equation that you need to use. So ui minus ue would come into picture, so it will become minus 90 because ue minus ui was 90, so ui minus ue would be minus 90, right? Just substitute the value of ui, ue, pressure, the specific volume, vi, ve already given, then gz is e, gze. So just substitute it. Q dot is also given, then you easily get w dot. Okay, try it out, then we can look upon another question. One more minute, then we'll look into the solution, then we'll try the next question. Okay. So I think we can look into the solution. So let us go to the solution once. I hope you tried. So let us look into the solution. Which question was this? So, yes, this is the one, right? So trying sir, please solve. Okay, thank you. You can go look to the solution once. Just cross verify. You can continue with your calculations, but just try to cross verify it with the solution that I have written on the screen. Then you can let me know whether you understood or not. Okay, take your time. It's fine. So, did you understood the solution? It was simple substitution. So the key was actually in this part that we need to, since all terms are in kilopascals, sorry, kilojoules. So you need to convert it as well into kilojoules. So we need to multiply it with 10 to the minus 3 uh, to have in terms of kilojoules. Okay. So once you do that, you will easily find the right work interaction is minus 122 kilowatts. Okay. Is that clear? Can we proceed? Okay, thank you. Let's look at the next part of the question. The next part of the question was find the ratio of the inlet diameter to the outlet pipe diameter. Okay, inlet pipe diameter to outlet pipe diameter. So so the key is here, since we know the velocity and the specific volume, then we can easily find the mass flow rate, right? So, and since the mass flow rate is equal at the inlet and outlet, then we can easily compare the diameters, right? So that's the crucial trick here. So if we do that, we will get that m dot will be equal to a1 v1 rho 1. So rho 1 would basically 1 by v1 small v. So a1 v1 by small v1 would be equal to a2 v2 into small v2, because the flow is steady. So the m dot e would be equal to m dot I. So that's what we have used there. So we use the generic m dot would be equal to a1 v1 by small v1 equal to a2 v2 by small v2. Then a1 by a2 would be equal to v2 by v1. So we just take a2 in the denominator and v1 here. So v2 by v1, and this will go up. So we'll have v1 by v2, right? Then we know that a area of a circular pipe cross section would be given by pi by 4 into d square. So if we do that, just we cancel out the pi by 4 factor, and we'll have d1 square by d2 square will be equal to 5 into 7, because velocity at the outlet was 5 meter per second, at the inlet was 7 meter per second, into the specific volume at the inlet was 0.95 meter cube per kg, and the specific volume at the outlet was 0.19 meter cube per kg. And once you do this calculation and take the square root of it, you will get that d1 by d2 is equal to 1.89. Is it clear? Okay. Okay, then let us go to the next question. Uh, yep, this is interesting one. Okay. A certain water heater, let's do question number 5. Okay. A certain water heater operates under steady flow conditions receiving 4.2 kg per second. So this is your m dot. Okay. 4.2 kg per second of water at 75 degrees Celsius temperature, and enthalpy of 313.93 kilojoule per kg. So this is your H1. The water is heated by mixing steam, which is supplied to the heater at 100.2 degrees Celsius and an enthalpy of 2676 kilojoule per kg. Okay, I will draw a diagram so it will be more understandable for you. So this is H2. Okay, so this is a problem related to the heat exchangers, right? Because you are saying that it is shown that water is water is coming in through at some inlet at an enthalpy of 313.93 kilojoule per kg, and again it is mixed with steam to raise its temperature, and where the steam is coming at an enthalpy of 2676 kilojoule per kg. Okay, so this H2. The mixture leaves the heater as a liquid water at temperature of 100 degrees Celsius and an enthalpy of 419 kilojoule per kg. So you clearly see that the enthalpy of water has risen up. So the purpose of heating the water has been achieved by mixing water and steam at different temperature at different enthalpy levels. Okay, so you need to find the how much steam must be supplied to the heater per hour. So you need to find m2 dot. Okay, so let me draw a diagram. So it will basically be something like this. So water is coming in at a particular mass flow rate, say m1, and an enthalpy of h1. Steam is coming at an enthalpy of m2 dot and some enthalpy h2 dot, and it is going out through the outlet. This mixture is going out through an outlet with a mass flow rate of m3 dot and an enthalpy of h3. So the key terms to know here is that your m1 is given h1, sorry, let me just write it out. m1, h1, h2 and h3 is given. So question is to find m2 dot. Okay, so I'll give you one clue. First clue is use the governing equations for a heat exchanger, because this is essentially a heat exchanger. Okay, so you need to use the concept of heat exchangers. Second clue is since the system is at steady state, you will have m1 dot plus m2 dot, because these two mass flow rates are entering the system, and this should, and since these streams are mixed together, so the net mass flow out of the system would be equal to m3 dot. So m1 dot plus m2 dot should be equal to m3 dot. So these are the two clues in your disposal. You can use them and then find the value of m2 dot. You need to find the value of m2 dot. Use the principle governing equation for heat exchanger. If you recall, it was something like m1 dot m1 dot h1 input is, it will be equal to m3 dot h3, right? Why? Because we know that for heat exchangers it was summation of m dot, let me write somewhere else, summation of, sorry, m dot I hi was equal to summation of m dot e he, right? So incoming streams are these two, so these two will come clubbed together here, and the outgoing stream is this one, so it will be included here. So you need to use these two equations to find the value of m2 dot. Have you understood the problem and the given clues? Just try it out, it's quite simple. I'll give you say 4 more minutes to solve the question, and then we can look into the solution. m3, yeah, m3 is not given, so m3 would be equal to m1 plus m1 dot plus m2 dot. So if you look closely, you don't even need to find m3 dot, because you substitute m3 dot as m1 dot plus m2 dot. So you will be left with m2 dot as the unknown, and then you can solve it. Okay. So since you have recently joined, let me just reiterate the question to you. So we are solving question number 5. So it is let me just look into it. Srinivas, you can just continue with the solution. Okay, I am just reiterating the question for the new student. So the question is: a certain water heater operates under steady flow conditions, receiving 4.2 kg per second of water at 75 degrees Celsius, an enthalpy of 313.93 kilojoule per kg. The water is heated by mixing the steam which is supplied to the heater at 100.2 degrees Celsius and an enthalpy of 2676 kilojoule per kg. The mixture leaves the heater as a liquid water at temperature of 100 degrees Celsius and an enthalpy of 419 kilojoule per kg. So we need to find how much steam must be applied to the heater per hour. So the schematic diagram for the problem is given here. So the water enters at a mass flow rate of m1 dot and an enthalpy of h1, and steam is being given into the control volume at a mass flow rate of m2 and h2, m2 dot and h2. Okay, enthalpy of h2. So these two streams of steam and water mix with each other, and the outgoing flux of fluid is at a higher enthalpy of h3 and a mass flow rate of m3 dot. So the question is, you need to find m2 dot. Okay, in the question we already have m1 dot, h1, h2 and h3 in hand, and I mentioned that through mass conservation you can easily say that m1 dot plus m2 dot would be equal to m3 dot, because since it is a steady state process, right? So And again, if we use the steady flow energy equation, the governing equation that we will have in our hand will be simplified to this form, that m1 dot h1 plus m2 dot h2 is equal to m3 dot h3. So we need to use these two equations to find the value of m2 dot. Okay, given that m1 dot h1 h2 and h3 are already given. So that's the question. You can try it out. Let's stop for 2 more minutes, hoping that Srinivas will solve the problem, and then we can look into the solution. So yes, 0.19. Yes. So if you look into it, it says 0.19 kg per second. Can you convert it into kg per hour? Question is asked heater per hour, right? Steam must be input per hour. Answer is actually correct. Okay, just convert it into per hour. Just multiply it with 36,000, 3600. You'll get the solution. Okay, then it seems that the solution has already been found out. Yes, exactly. Thanks, Srinivas. Srinivas, I hope I am pronouncing it correctly. Forgive me if I'm wrong. Okay. Okay. So let us look into the solution. I hope, which one it is? Yeah, it is this one. Right. So as I mentioned, this is a diagram that we had in our for the question that we had in consideration. Question number 5. So by mass balance, you can write I used m1 dot here. I am using w1 here. So w1 plus w2 is equal to w3. Okay, it comes from the mass balance. From the energy balance, you will have that w1 plus h1 plus v1 square by 2 plus gz1 plus q dot equal to w plus w2 h2 plus v2 square by 2 plus gz2, because there are two inlets, so you need to consider both of them, would be equal to w3 plus h3 v3 square by 2 plus gz3 plus w dot. Okay, here both heat and work interactions are 0. I have already explained why heat interaction is 0, because this heat interaction is primarily between the system and the surrounding, and the purpose of heat exchanger is to have heat interaction within the system between the streams of fluid that comes into interaction. Okay, so this q dot would be 0. Considering that the kinetic and the potential energy are negligible, so our governing equation is simplified into w1 h1 plus w2 h2 plus w3 h3. And from the mass balance, we get that w3 is equal to w1 plus w2, so we substitute w3 as w1 plus w2. So from that we have that w1 h1 plus w2 h2 is equal to w1 plus w2 into h3. So just substitute the value of h1, h2, h3 and w1. So we'll get 4.2 into 313.93 plus w2 into 2676 is equal to 4.2 plus w2 into 419. So the only unknown left here is w2. So once you solve for w2, you will get that w2 is equal to 0.196 kg per second or 705 kg per hour. Okay, just multiply this with 60 into 60, so we will get 705 kg per hour. I hope that's clear. So let us look in the next question. Which one should I? Okay, let us take this one. Question number 7. Okay, this is related to the steam tables. So I am just for saving time, I'm using question number. Let us focus question number 7. Okay. In a steady flow apparatus, 135 kilojoule of work is done. Check the units. Okay, it's kilojoule of work, so it is total work rather than work done per unit mass. Okay, so 135 kilojoule of work is done. Work is done by each kg of fluid. Okay, so work is done by the system, so it is positive. So and kg of work is done by each kg of fluid, so this basically becomes, so we will have w dot as well as 135 kilojoule per kg. Okay, this is a trick of finding out how to find out w dot. So w dot would be 135 kilojoule per kg. Okay, the specific volume of fluid, pressure, velocity at the inlet are, this is small v1, this is p1, this is v1, capital V1. Okay, this is velocity. The inlet is 32 meter above the floor. So Z1 is 32 meter above the floor, and the discharge of the pipe is at a floor level. So Z2 is 0. The discharge conditions are 0.62. This is again your V2, small v2. This is P2 and this is V2. Okay, velocity. The total heat loss between the inlet and the discharge is 9 kilojoule per kg of fluid. So this is Q, which is minus 9 kilojoule per kg. In flowing through the apparatus, does the specific internal energy increase or decrease, and by how much? Okay, so you need to find out U2 minus U1. Okay, is the question clear? It's again quite simple. It's just the application of the entire steady flow energy equation. Substitute the given values and find the net change in the internal energy. Is it clear? Okay, so let me give you say 6 minutes, say up to 7:48. Try it out. One more key thing I will let you know is that while measuring the kinetic energy, just if all your energy terms are in the form of kilojoules, because your work done is at kilojoule, your energy output is at kilojoule, and your pressure, where you use the term PV, right? PV to find the flow work. H is equal to H is equal to U plus PV, right? So PV here, P is, since it is in kilopascal, so PV would give something that is in terms of kilojoules. Okay, kilojoules per kg. So since all your terms are in kilojoules per kg, make sure that you convert your net change in kinetic energy and the potential energy into kilojoules as well, okay, by multiplying it with 10 to the minus 3. Okay, then let's wait for 5 more minutes and then see the solution. This is the last question for today. Then we'll do the match the following one and then it will be finished. Okay, so try it out. So let me also try to write. So since all terminologies are in mass per kilojoule per kg, so let us write the equation in that form. So small q dot plus h1 plus v1 square by 2 plus gz1 will be equal to w dot plus h2 plus v2 square by 2 plus gz2. The key thing is to convert h into the sum of the internal energy and the flow work. So we can write so let me write it in this way. So q dot minus w dot plus v1 square minus v2 square by 2 plus g z1 minus z2 plus P1 V1 minus P2 V2 would be equal to U2 minus U1, and this is what you need to find. So just substitute the value of Q dot W dot V1 square V2 square, Z1 Z2 and P1 V1 and P2 V2, and then get the solution. Okay. It's quite simple, just simple substitutions of the given values, then you will get V2 minus U1. 2 more minutes, then let me see the solution from your end, and then you can proceed. Do you need some more time? Okay, let me wait for 2 more minutes. Two 93.598. Okay, let me check. Hmm. Uh, okay. It seems just asking. Okay, have you multiplied 10 to the power minus 3 into the with the potential energy and the kinetic energy term? Okay, now let me just check from my end as well. Okay, you just verify it once. If yes, then just tell. Otherwise, I'll try. Okay, just one second. Uh, 'Okay, so let me just verify. Okay, so this term, sorry, this terms out to be minus 160. Okay, let me then 32 into 9.81 into 0.001 would be 0.314. 314. The kinetic energy term, you just cross verify with me as well, okay? Let us just try to do it together, this one. So 270, V1 is, what's V1? V1 is 16, V2 is 270, right? So, okay, 653.598. Uh, okay, so I'm just verifying myself as well, okay? Just forgive me for delay. So, V1, okay, okay, okay. Right? So this is actually positive. This is also positive. This is 16 square minus 270 square divided by 2 into 0.001. It will be minus 36.32, and Q dot is minus 9 minus 135. Is it by each kg? So let me just add it up. Minus 9 minus 135 minus 36.32 plus 0.314 plus 160. So it turns out to be minus 20. U2 minus U1 is minus 20.006 kilojoule per kg. So I get this one. So, and I guess this is something that I got the calculation that I also did. So did you understand it, or there was some error? Let me just show you the calculations, maybe that might be helpful. So I guess I did it. Explain it, sir. Okay, sure. Let me just explain it. I'm trying to find the calculation that I did. Oh, this one. Yeah. So let us go through each step. So at the inlet we have 0.37 meter cube per kg. P1 is 600 kilopascal. Check the units. Units are very important. Okay. P1 is 600 kilopascals. V1 is 60 meter per second. Z1 is 32 meter. Q is coming out of the system is minus 9 kilojoule. The work is done by the system, so it is 125 kilojoule positive. Okay. V2 is the specific volume. Okay. 0.62 meter cube per kg. P2 is 100 kilopascals. V2 vector, which is velocity, is 270 meter per second, and Z2 is 0 because it is at the ground level. So from the steady flow energy equation, we have U1 P1 V1. I just dissociated the enthalpy in the form of the internal energy. So U1 P1 V1 plus V1 square plus Z1G plus Q dot is equal to U2 P2 V2 plus V2 square by 2 plus Z2G plus W dot, because all terms were in the form of per kg, so I just divided it by M dot. Taking that mass conservation would give M1 M dot E is equal to M dot I is equal to M dot. So I will divide it by M dot to get this form. So I want U1 minus U2, right? How, as the internal energy increase or decrease, we need to find a difference between the internal energy and final internal energy and the initial internal energy. Okay. So I take U2 in the left hand side and all these terms in the right hand side. So you get U1 minus U2 as P2 V2 minus P1 V1 plus V2 square minus V1 square by 2 plus Z2 minus Z1G plus W dot minus Q dot. So P2 would be 100 kilopascal. If I just zoom out a bit, so P2 is 100 kilopascal. 100 into 0.62 specific volume minus 600 into 0.37, 600 into 0.37. Then V2 is 270, then 270 square minus 16 square, the velocity into 2 divided by 2 into 10 to the minus 3. This is because all these terms will give energy in the form of kilojoule per kg. But if you don't multiply this factor, you will get it in terms of joules, right? So relation between joules and kilojoules is 1000 times the joules, right? The value of joule. So, or 1000 joule is 1 kilojoule. So, we to divide it, multiply with 10 to minus 3 to get this value in terms of kilojoules. So, similar thing we have to also do with the potential energy term. We multiply it with 10 to minus 3, and finally work done is 125, which is positive. Work is done by the system, minus q load. So minus 9, because heat work is going out of the system, right? So minus 9. So once you substitute, um, put all these values and calculate it, you will get that u1 minus u2 is 20.136 kilojoule per kg. So is it clear now? Okay, so let us do the last question. Simple match the following. So uh, it's something that we already did. So all these expressions correspond to one of them. Okay, we discussed nozzle and diffusers, turbines and rotary compressors, heat exchangers and adiabatic throttling. So you just need to tell me which is the right choice, which one is matched correctly. Okay, the steady flow energy equation for the corresponding, okay, corresponding devices. So you say 2. So 2 is AQ. A is Q, correct. B is P, turbines, rotary compressors. B is P. Oh, this is not correct. This should be, oh, right. No, this should be this one, right? B should be S. B should be S, so this is correct. C is R. C is R. No, heat exchanger should be P, so C should be P. D is S. D is S. No, adiabatic throttling will give HI equal HE, so D is R. So option 1 is correct. Is it clear? It's a simple match the following for the steady flow energy equation for the concerned devices. It's just you can recall it. That's fine. So is it correct? Is it fine? Okay. Okay then. Thank you so much for attending the class. Thank you for great interaction, and that's all for today from my side. And thank you. Thank you so much. I hope the interaction was helpful.